Good afternoon, everyone. This is Group
5.
And my name is Tariq Powell.
India McCall Taylor.
Casey McIntyre.
Deja Mickens.
Kamani Ridley.
And this is our Neuron story.
Alright, so an event happens in cell A where the neurotransmitter is released into the synapse of the cell B, specifically speaking regarding the neurotransmitter release exocytosis. The synaptic vesicles from cell A button from exon branch bind to the presynaptic membrane where they split open, causing an opening in the presynaptic membrane. The neurotransmitters are then released into the synapse where it travels across to bind the receptors in the postsynaptic membrane, dendrite, and cell B in a key lock fashion. The postsynaptic membrane is made of a lipid bilayer and the cytoplasm is located on the inside of the cell, whereas the interstitial fluid is surrounding the outside of the cell, and the receptor expands in order to receive the neurotransmitter.
All right, so now we're going to go kind of in depth on how the cells look. And we're going to go with cell B, since it's the biggest form. Cell B is started off with the soma, which is also known as the cell body. And inside the soma is the nucleus, it starts in the middle. Outside of the nucleus, which just go throughout the whole cell body, is cytoplasm, as stated earlier. On the outside of the cell body, or the soma, is dendrites. They are like little branches, thank you, branches on the cell body that receive the electrical transmission. Also connected to the cell body is the axon hillock, where the neurotransmitters are sent through, that goes down through the axon shaft, where the neurotransmitters bounce from node, river, Van Veer, from node to node, where it starts with time 1 in the axon shift, has the action potential and the axon hillock from the first to the second to the third, and are at rest as well as the terminal buttons. That's when it reaches here. Time 2, the axon hillock has returned to the rest, but the action potential has moved to node 1. At time 3, the action potential is at node 2, and the action potential has reached the terminal buttons and the interaction with calcium, so that the synaptic vesicles from cell B binds to the inside of the presynaptic membrane, which is here. This is where the synaptic vesicle splits open, causing the opening of the presynaptic membrane. The neurotransmitters are then released into the synapses where it travels across to the bind side receptors and the postsynaptic membrane, and the dendrites in cell C and the key lock. So this all synaptic buttons. This is where they sit and are ready to release into the next, to the synapses to get to the next cell. And where it happens, where this is all the synapses stuff, where it gets to the next cell, that is called dendritic hybridization.
Okay, when the receptor is open, when it's trying to bind, when this dendrite, when it's trying to bind, the neurotransmitter is trying to bind to the dendrite. It causes an opening in the cell, which is cell B, and it causes sodium to be able to enter into the cell through osmosis and electrostatic pressure. The cell wants to become more positive, and it's more positive on the outside than it is on the inside of the cell. So once sodium moves into the cell, it reaches equilibrium.
And sodium moves from a high to low concentration. So once the high concentrated area, once the opening happens, the high concentrated area flushes up and goes into the low concentrated area, like she said.
your process of osmosis.
Okay, so I'm just gonna break this down a little bit more. So the graph, it registers at negative 70 millivolts. That's the cell at rest. An EPSP is the little bump, which brings it to negative 65 millivolts, and that's the threshold excitation, which initiates the action potential. After the action potential is initiated, it starts something that's called temporal summation, which is the major depolarization of the cell, which means there's more positivity going into the cell, which is why there's a high rise like that. That means there are so many neurotransmitters binding to the same binding site that it opens up that way. Let me see what else. An EPSP is created when ionic trophic, where is it? Could they do it? Oh, ionic trophic receptors are located on dendrites of cell B are open due to the presence of neurotransmitter binding. Let's see. The location of receptors that cause threshold excitation are at the axon hillock, which is right over there on cell B. The axon hillock collects the consummation of all the small electropotentials. They add together at the axon hillock and cause the opening of voltage-gated channels. The channels look like ionic trophic receptors, however, there's nowhere for neurotransmitters to bind because there's no transmitter involved. Voltage-gated channels require that multitude of voltage provided by many neurotransmitter binding sites being open. Once the negative 65 millivolt threshold is reached, that is the initiation of the action potential, as I already said. It is generated for rest, and that causes the massive influx of sodium into the cell, which she just talked about, how it's trying to get from high to low concentration, and so much sodium in the cell that it goes to positive 55 millivolts. And that's the massive depolarization. The sodium reaches equilibrium and the potassium gates open. And since the cell is now positive and potassium is also positive, there's more potassium inside the cell than outside. The charges repel each other and potassium leaves the cell, which is the hyperpolarization. That's losing positivity. And this is the downswing on the oscilloscope graph. When potassium reaches its equilibrium point at negative 75 MV, the sodium-potassium pumps bring the cell back to rest.
So the action potential obeys the all or none response law because it must be continued to completion. So it starts at the axon hillock, and when it reaches the myelin sheath edge, it spreads like a wave-like motion to each node around here. So from time 1 to 2 to 3, and each node has a particular potassium-gated channel and a sodium-gated channel, which allows sodium in and potassium out at each node. And this is called saltatory conduction. So after it reaches time 3, it will go towards the terminal buttons where it interacts with calcium so that synaptic vessels from B bind to the inside of the presynaptic membrane, and vesicles split open, causing the opening in the presynaptic membrane, and the neurotransmitters are released in the synapse where they bind to the receptors and HELOC action to cell C.
Just a quick fun fact about these cells and certain things that can happen. From cell A to cell B, there's 4 possible solutions that may happen from while the neurotransmitters sit in the buttons at resting point. A possible solution would be the neurotransmitters get sent back up through the axon hillock, or the axons and through the terminal buttons, which would be called reuptake. Or the neurotransmitters can get sent through and released, but however never reaches the dendrites, and that means it gets kind of floated away in the interstitial fluid, which is called
Dissipation.
dissipation. Yes. Then 3,
It can be metabolized by enzymes.
can be metabolized by enzymes, and last but not least, of course, they can make it into the next dendrite and bind. And that is the neuron story.